So now we want to talk about some physics applications, and we're going to start by taking a look at the position and function. This came in, we saw it, I believe it was around section 2.2, where we were introduced to the shortcut rules for differentiation, and we're going to ask the question, where did this guy come from? Well, here's what we know. Let's start with what we know. We know that acceleration is some constant value, and we're talking about on Earth. So, and I'm going to be very generic here. I'm going to call it the gravitational force G. We also know that in the beginning we had an initial velocity. So at time 0, the velocity was something, and we may not know what it was. So we're going to be very generic and call it V naught or V sub 0. And we also know that in the beginning, this thing, whether it's a ball or a coin that we're dropping, started at some initial height. I'm going to call it S sub 0. And remember, I'm using the cursive S's to separate my S's because my regular S looks a lot like a 5. So I'm using the cursive notation here. So we also know of something else. We know a few other things, actually. If we were to take the derivative of the position equation, then we're going to get velocity. And if we were to take the derivative of velocity, which is really the second derivative of the position, then we're going to get acceleration. So we can kind of use that to get backwards. Well, if we integrate acceleration, if we were to integrate acceleration, this guy, then we would have to get back to the velocity. And if we integrate velocity, then we're going to have to get back to the position equation. So we're going to use that, all of these ideas, and kind of put everything together into one place. And then we're going to end up actually being able to derive where this guy comes from. So let's do it. If we integrate acceleration, and I'm just going to use A for acceleration here, and keep in mind we're doing everything with respect to time, because we're talking about how long something falls, or if we throw something off a building, how long does it take for it to reach the ground? So how long would be a time? So if we integrate acceleration, remember our acceleration is this constant number G. So we're integrating G. We're integrating that function, and I could use the function notation and then do that substitution here. If we integrate G, then we're going to get G times T. Because remember, we're integrating with respect to time. This guy's just some number plus some constant. So just to kind of recall, it depends on if we are in feet per second or meters per second. But if we're dropping something off a building, or if we're throwing something up in the air, gravity acts as a downward force. So it's negative. It's either negative 32 feet per second squared, or it's negative 9.8 meters per second squared. So using that generic value of G allows us to be able to plug in any of these numbers in here. And in fact, if we wanted to, we could take this off Earth and we could talk about it on Mars or on the moon, anywhere where the gravitational force would be a little different. But as long as we know that, this would work. So now we've got this, and remember, this guy's going to be the velocity. So here's our velocity equation, but we've got some kind of constant here. We got to figure out what that guy's going to be. Well, we're going to go back to those initial conditions. We said that at time 0, we had some initial velocity, and it's that velocity V naught. So let's substitute that information in. If we substitute that in, then our velocity was v sub 0, and we're plugging 0 in for that t. So then our v naught is equal to c. So then our velocity equation is gt plus v naught. Well, that's nice, but now that we have velocity, we want to get back to that position equation. So we could integrate both sides here to get back there. And if we do that, when we integrate velocity, we will get the position equation. And remember, we are integrating with respect to t here. It's important to remember the variable. So this g, that's just a number. This initial velocity is just a number. So we're going to have g times t squared over 2 plus that initial velocity times t plus some kind of constant. So I'm going to rewrite this guy just a little bit. So you can see where that equation from section 2.2 is starting to come from. Now we just have to figure out what c is. And we're going to use that other piece of information, that initial value for that height. So if we were to make our substitution here, we said the initial height was some value, s naught. And we're substituting 0 in for t because that was the time where that happened. So if we were to simplify this, 0 times anything is 0. So those two guys are gone. We're left with s naught is equal to that constant. So then our equation, s of t, is equal to 1/2 gt squared plus v naught t plus s naught. Okay, all we're doing is substituting that s naught in for that c value. So you can see where this equation's coming from.